Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss bonding in coordination compounds. Last class I have finished isomerism. Now I am going to start bonding in coordination compounds. Werner was the first to describe the bonding feature in coordination compounds, but his theory could not answer basic questions like first, why only certain elements possesses the remarkable properties of forming coordination compounds. First objection I am telling you, or limitation. This is called drawback. These three these things are there. Questions are there that you can tell. These are the drawback of Werner's theory or limitation of Werner's theory. Question is asked, or failure of Werner's theory also you can tell. Three terms are used. Then first was that why only certain elements possesses the remarkable property of forming coordination compounds. Second, why the bonds in coordination compounds have directional properties. And third, why coordination compounds have characteristics, magnetic and optical properties. These three questions was not answered. These are actually basic questions which was not answered by Werner or by Werner theories. Many approaches have been put forth to explain the nature of bonding in coordination compounds, as for example, valence bond theory, VBT. Second, crystal field theory, CFT. Third, ligand field theory, LFT. And fourth, molecular orbital theory, MOT. Okay. Many approaches have been put forth to explain the nature of bonding in coordination compounds. Then I told four names. First is the valence bond theory, VBT in shortcut, VBT, valence bond theory. Second, CFT means crystal field theory. Third, LFT, ligand field theory. And fourth, MOT, molecular orbital theory. These theories were explained. These theory, actually these are the approaches you can tell. These are the approaches which have been put forth to explain the nature of bonding in coordination compounds. When Werner's theory failed, and it has a limitation, three limitation I told you, then these theory came, and these theory actually, or you can tell approaches. These are the approaches. These three are the approaches have been put forth to explain the nature of bonding in coordination compounds. Because Werners were not able to explain all these three questions. What were that three questions? Again I am telling you. Why only certain elements possesses the remarkable properties of forming coordination compounds. And second, why the bonds in coordination compounds have directional properties. And third, why coordination compounds have characteristics, magnetic and optical properties. Then now this theory came, I will discuss one by one. Okay. Valence bond theory. Valence bond theory question is also asked. Many question is asked based on valence bond theory, VBT. According to this theory, the metal atom or ion under the influence of ligands can use its n-1d ns np or ns np nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar, and so on. Here main thing is that orbitals you can tell orbitals in the orbitals of the metal atom or ion, central metal atom or ion, its orbital. What are there that orbitals? Then you know that metal atom or ions under the influence of ligands, because ligands approach to the central metal ion, then what it will do, these ligands when they are coming towards central metal ion, then what will be its effect, what will it do? Then I am telling you that under the influence of ligands, these ligands can use this metal atom or ion. It may have d orbital, n-1 d orbitals, ns orbital, np orbital, n-d orbital, ns orbital, and np orbitals, or ns, np, or nd. These orbitals of the metal atom or ion, they will mix. Means you can say these orbitals will hybridize. Hybridization will take place. Why hybridization will take place? Actually, what is the hybridization? Hybridization is the mixing of different orbitals. To give orbitals of equivalent energy. Because in the beginning, these orbitals, as for example, n-1 d orbital, ns orbital, np orbital, they have different energy. Then after mixing, they will provide equal number of orbitals having equivalent energy. Total number of orbitals will be the same. If you will count d orbital, s orbital, p orbital taking part in the mixing or hybridization to give orbitals of equivalent energy, in the same number of orbital you will get, but energy will be almost equivalent, not equal. Then this is actually called hybridization. Then here n-d, n-1d, ns, np, these can take part in hybridization, or ns, np, and nd orbitals can take part in hybridization. Okay. And what is the purpose? To yield a set of equivalent orbitals of definite geometry. Then what? They will form a geometry. These orbitals, they will have equivalent energy first, and you can say this thing, geometry also, to yield a set of equivalent orbitals of a definite geometry shape, what we can tell, definite geometry such as octahedral, tetrahedral, square planar, and so on. These orbitals, these orbitals after hybridization, it is called hybridized orbitals. Means orbitals of equivalent energy having definite geometry are called hybridized orbital. Then these hybridized orbitals are allowed to overlap with ligands. Correct? After this, you got now hybridized orbitals of equivalent energy having definite geometry. After that, what will happen? These orbitals are allowed to overlap with ligands orbitals that can donate electron pairs for bonding. Means first hybridization, after that ligands will overlap. Means they will provide pair of electrons. Okay, these are hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. Okay, now I am telling you just example. Just to consider coordination number 4. Then coordination number 4 means 4 bond is there. Means 4 if it is a unidented, then 4 ligand will be there. Unidented, if ligands are unidented, then 4 ligand. Actually, you know that coordination number is the actually number of bonds making with central metal ion or central metal atom. Then in coordination number 4, what will happen? Total 4 orbitals are there. Then what will be hybridization? Then 1s and 3p. 1s and 3p. Then types of hybridization will be sp3. 1s 3p. Then total 4 orbitals, and all 4 orbitals will be called sp3, 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 sp3. All are equivalent. And these sp3 hybridization, then what will be the geometry of these orbitals sp3, 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 sp3? What are their geometry? Then distribution of hybrid orbitals in a space. What type of geometry it will give? Then it will give tetrahedral. If coordination number is 4, then types of hybridization will be sp3 and geometry will be tetrahedral. Now 1-2 situation is there. If coordination number is 4, first it may be tetrahedral. Second, if coordination number is 4, then other possibility is also there. But in that situation, hybridization will be in another name. Another name means DSP2. Total 5 only, a total 4 only. DSP2. This D is n-1D, inner D orbitals. n-1 D. Okay, whatever D is there, D may be, we can say incomplete, means back also inner, that is called inner, and you can say ahead also, SPD, that is the in a normal way. But before the S, you have seen sometimes D will be not filled and S will start. D is not filled and S started. Then this is called inner, n-1 D. Same thing will happen with F also. That F has an F will not start, and then this F will be not filled, and then SPD started. SPD may start without filling F. Then that situation also, same situation will be there. That is the n-1 F. Okay, but here come to the N. Then here, if coordination number 4 is there, then one more possibility is there. That hybridization will be DsP2. Means now in hybridization, inner d orbital has taken part. Inner d orbital has taken part, not the outer, inner. Then one inner, and after that inner d orbitals, and then s orbital, and then p orbitals. Then there are three p orbitals, px, py, pz. S has only one. But here one d orbitals, one s d orbitals, one d orbitals, and s orbital, and two p orbital has taken part. Total 4, d, s, and 2p. Then it became dsp2. Hybridization is dsp2, and this time it's in a space. Its arrangement will be, means it will give a geometrical space, different geometrical space, that is called a square planar, in a square form, and they are in a plane, one plane, means on the paper only, not up, not down. Okay, but in a space you can see that all are in one plane, just like on paper you can write, and it can be on paper. Okay, then that is called a square planar. Then two situations are there for coordination number 4. One is sp3, another is dsp2, but total 4 only. Then sp3 is called tetrahedral, but dsp2 is called a square planar. Now next you come to the 5. If coordination number 5 is there, then here will be sp3d. Hybridization will be sp3d, means total 5. 1 s, 3p, and 1 d. But this d is outer d. Okay, then sp3d, and here total 5 is there. Then 3 out of this 5, 3 will make a trigonal shape, 3, and 2 will be just perpendicular like that, means central metal ion, means one will be upside, other will be down, up and down, and 3 orbitals will take a shape of triangle. It will take a shape of triangle, and that's why it is called trigonal bipyramidal. Trigonal, bi means 2, then because one is up, other is down, it is taking the shape of pyramidal, and it is making two pyramidal. One upside you can see, it is, if you will not see down orbital, then it will look like a pyramidal. Okay, if you join all orbitals except down, then it will be one pyramidal. But if you will consider down also orbital, then it will make a 2 pyramidal. That's why it is called a trigonal bipyramidal. Bi means 2. Now if 6 coordination number is 6, means 6 bonds are there. 6 bonds are there. With central ligands has made 6 bond with central metal ion. Then now here again 2 cases are there. One in a general way, sp3d2. Total 6, 1 s orbital, 3 p orbital, and 2 d orbital. Then s orbital 1, p is 3, and d is 2. Total 6. 1 plus 3 plus 2, 6. Then now it will form octahedral. Its geometry will be called octa, means 6. Octa means 6. then sp3d2, D is outer, then it is octahedral. One more octahedral will be formed when coordination number is 6. Now you can write D2sp3, D2sp3 means inner D. Now this time inner D has taken part in hybridization with S and P. 2 D orbitals, 1 S and 3 P, then D2sp3, and it is also called octahedral. Okay, octahedral. Then this I have told you about the these things, geometry with coordination according to the coordination number and hybridization. Now I want to tell these things, I want to explain on the basis of electronic configuration. Okay, then by taking example of cobalt. Okay, cobalt NH3 whole 6, cobalt NH3 whole 6 ligands are there, all are NH3, and on the complex 3 plus charge is there. Okay, outside 3 plus charge is there. Then here we consider first cobalt orbitals. You can write electronic configuration. You write electronic configuration of cobalt 3 plus. Cobalt 3 plus means 3 electron you minus it. What is the atomic number of cobalt? You minus 3. Okay, atomic number of cobalt minus 3. Okay, then you will find that in outside in d orbital, now total how much you will get? 6 ligands are there, cobalt NH3 whole 6. Then 6 I can say d orbitals you have to consider, 6 d orbitals for cobalt 3 plus. Then you can write 3d 4s 4p. Okay, and the last I am writing only for d, last orbit d. Then in d total how many electrons are there? Then it will be 6 electron. Then vacant also you can write, whether it is used or not, you write the vacant also. 3d 4s is vacant, 4p is also vacant. Simply you write. Why you will write? It is now filled only in d. Then why you are writing for 4s and 4p? It is empty, vacant. Then you will write because in hybridization vacant will also take part. Okay, sometimes vacant orbitals or incomplete S or incomplete P can take part in hybridization. That's why it is written. Means electron can, after the excitation, electron from the d, suppose it is a paired. Suppose in d orbital 5 orbitals are there, d5. 5 are there, dxy, dyz, dzx, dx square minus y square, dz square. 5 are there. Then out of 5, maybe 1 or 2 filled. Filled means 2 electrons, rest are 3 electrons. Then actually what happens, this is a normal condition. But in excited means when you will heat it, or you can tell after getting energy, these 2 electrons which are filled, 2 electrons are having, it is a possibility that after getting energy it will jump to the, it can jump to the S and P also. It can go to the S also, P also. And after that hybridization will take place. 3 steps. Okay, first you can write normal, in a normal condition electronic configuration. Then after excitation, in excited state, what is the electronic configuration? And then in third step, that this will overlap. Ligand will come and then it will overlap. Ligand will donate electron in third step. Correct? And molecule will be formed. Then here in the first step, in normal condition, its electronic configuration is 5 electrons are there, then one electron filled in all 5, and after that, according to the Hund rule, 6 electrons are there. The first one electron it filled, it went in all 5. After that, pairing started. Then it come to the first D, and it is paired. Then now out of 5 d orbitals, one is filled. One is filled, other 4 are only one, single. That is called unpaired. And 4s is vacant, 4p is vacant. Okay, 4s is vacant and 4p, 3 orbitals are there, 4p, px, py, pz, all are vacant. Then now in excited state, what will happen? When energy will be given, after getting energy, it will be excited. Then now it will what will happen? Then now only in D orbitals, they themselves will rearrange and it will form actually not D, S and P, all three will you can say these things take part in hybridization. D also, S also and P also, all three will take part in hybridization. And here one thing you have to remember, very important, that now D, 4 orbitals have unpaired electron, one, single. Then now these out of these 4, what will happen? These will be paired only among themselves. Inside the D only, they themselves will paired. Means now this 4 unpaired was there, now it became, these 2 came and paired. Then now total 6. Now 3 d orbitals is filled, having 2 electrons. And means out of 5 orbitals, 3 orbitals now it is filled. 6 electron was there, then first, second, third. These 3 are filled completely and 2 are vacant. 2 are vacant d orbitals, and 3 are fully filled. Then now in hybridization, what will happen? That all you can say, all vacant d orbitals will take part in hybridization. Means 2 d orbitals, they don't have electron because that electron paired. Then 2 orbitals are now empty. 2 d orbitals are empty. 4s is already empty and 4p is also empty. Then now these empties, all empty, will take part in hybridization. This is very important. Empty also takes part in hybridization. Sometimes maybe having 1, 2 electron, but with half-filled orbitals also can take part in hybridization, and sometimes fully filled also, but that is less. But half-filled, it is a common. Half-filled orbital also can take part in hybridization. Okay. Then now here D, S and P all are empty and are taking part in hybridization. Then now this time it is a inner d orbital. 2 d orbitals are inner taking part. Then it will form D2sp3 hybrid orbitals. D2sp D2sp3 hybridization. 2 from the D and 1 S. S only one have one orbital only S and 3 P, hence D2sp3. D2sp3 total. Now it became 6 orbitals, 6 hybridized orbitals. Okay, and all 6 orbitals are now empty. Then what will happen in the last step? Ligand will come. 6 ligand will come, because total 6 hybrid orbitals are there. Then 6 ligand will come, and each ligand will donate 1 pair of electron. Means 2 into 6, each pair will 1 pair, means 12. 2 into 6, each ligand will donate 1 pair, means 6 ligand has donated 1 pair. Then now it formed the compound. Now compound is complex ion is formed. Okay, but here inner d orbital has taken part, and all orbitals are fully filled. Total 6 orbitals are there. D2sp3, all are called D2sp3, all orbitals. Their name is only same name, D2sp3. Then here you can see all are fully paired, 6 pairs of electrons from 6 NH3 molecules. Then now it formed, which complex it formed? It formed cobalt NH3 whole 6, 3 plus, because you have written electronic configuration after removal of 3 electrons. 3 plus means what? It has removed 3 electrons. It went outside. What was the remaining? For that you have written electronic configuration. Then now this I have told you, this is very, very important. What happens actually in the complex formation in VBT theory, valence bond theory. This happens actually. One example I have told you. Now I want to tell you magnetic behavior. I told you it is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior. I want to tell you about the magnetic behavior. From the magnetic behavior, it is possible to predict the geometry of a complex. Okay, how? On the basis of valence bond, actually from the magnetic behavior, you can know the geometry of a complex ion from the basis on the basis of VBT, valence bond theory. Now how we will tell magnetic properties? I am telling you. In the diamagnetic octahedral complex, cobalt NH3 whole 6, 3 plus, the cobalt ion is in +3 oxidation state. Okay, and has the electronic configuration 3d6, and here 6 pair of electrons, one from each NH3 molecules, occupy the 6 hybrid orbitals. Thus the complex has octahedral geometry and is a diamagnetic, and it is diamagnetic because of the absence of unpaired electron. This is important. If there is no unpaired electron, then complex will be diamagnetic. Remember, if it is unpaired, then magnetic. If there is no unpaired electron, then diamagnetic. Okay. In this case, this complex means cobalt NH3 whole 6 3 plus is a diamagnetic because of the absence of unpaired electron. In the formation of this complex, since the inner d orbitals means 3d is used in hybridization in the complex, it is called an inner orbital. Inner orbital and also called low spin. If inner orbital is taking part, inner orbital, then it is called low spin. Means now unpaired electron is not there, low spin. Or you can tell a spin paired complex, a spin paired. All are paired, all electrons are paired. Then low spin and a spin paired has same meaning. A spin paired and low spin. Okay. The paramagnetic octahedral complex, its example I am telling you, paramagnetic, that is the cobalt F6, cobalt F6 3 minus. This is another complex example I am telling you. You just name also you keep in mind, because limited number of complex ions are there and they have a special color also. If it is color, then it is colorful. Diamagnetic case, now all are filled, spin paired are there, there is no diamagnetic and no color. But if it is a magnetic, unpaired electrons are there, then it will show two character. First magnetic and second it will be colored also due to unpaired electron. This you remember. This is very, very important. Then example I am telling you, the paramagnetic octahedral complex, cobalt F6 3 minus. This complex uses outer orbital, 4d it will use in hybridization. Here also 6 orbitals are taking part. Here also 6 orbitals are taking part, d orbitals. Total 6 orbitals are just like cobalt. Here also 6 orbitals are taking part, means d, s and p. But here difference is that this time d is outer d is taking part, not the inner. In the first case I told inner has taken part, but now outer d is taking part. It means sp3 d2, sp3 d2. This is the here outer orbital has taken part, 2d orbital has taken part in hybridization. 4d, that is the 4d. Okay. In the first case it was 3d. Now in this case 4d. Both were present in that atom electronic configuration. Both were present. 3d also, 4d also. Okay. Then now 4d has taken part. And now in this situation, again you can write the electronic configuration, then you can understand very well. And now it is 3 minus. 3 minus means here now cobalt is 3 minus. In that case it was, first case it was 3 plus. Now it is a 3 minus. Then how will you write here? It means 3 electron it has taken. 3 electron it has taken. Minus 3 means what? 3 electron it has taken. Then whatever was the atomic number of cobalt, in that 3 you add and then you write electronic configuration. Correct? Then in that situation you will find But here I am telling you that complex is 3 minus. Complex is 3 minus finally. But here when you are writing electronic configuration, that meaning I told you 3 minus meaning means 3 you have to add. But here actually that 3 became due to the F electron. F has electronegative. Then 6 F electron came. Then it has given 6 electron, 6 minus. But 3 cobalt was 3 plus. Hence finally it became 3 minus. They neutralized 3 plus. They have given, the cobalt has lost 3 plus, that it got 3. And after that extra 3 it got. That's why it became 3 minus. 3 minus. Complex is 3 minus. But now here you have to write electronic configuration of cobalt 3 plus only. Cobalt 3 plus only electronic configuration you write, because in cobalt F6. Cobalt F6 outside 3 minus, cobalt has only plus 3 oxidation state. In this case also cobalt has a plus 3 oxidation state. That's why same way you have to write electronic configuration what you have written in the first case for CO and cobalt NH3 whole 6 3 plus, same way. Then here also you can say 6 electrons are there. Then here 6 electrons again you will write same way. One orbital is having 2, another 4 are 1 1 1, single. S, P and D is, you keep it as a vacant. 4s, 3D is a 1, D is a filled, 4 is vacant. Leave it like that only. Now 4s, 4p, 4d you also write. Now outer 4d also you write. Then now you can see what will happen. Then this time actually now hybridization will take with 4d means outer, not the inner, outer. Then now this time again it will form sp3d2. Now d you are writing in the end, d2. It became 6. Then all six are empty. All 6 are empty. And these 6 pairs of electrons, now who will give? Then fluoride ion, they have 1 negative charge, that you know. But what is the main thing, sir? This ion, fluoride ion, have a lone pair of electron also. 3 lone pair of electrons they have. 7 electrons are there in fluorine, outermost orbitals, 7. Then now 3 pairs are there. 3 lone pair of electrons are there. Then from that each fluoride ion will give one can say lone pair to the vacant d orbitals. 6 vacant d orbitals are there. Then each fluoride ion will give one lone pair. Correct? And already they have 1 negative also. That due to that it is neutralized. 3 plus is neutralized, and now it got 3 negative. But now here all 6 F will give, fluoride ion will give one pair of electron, total 12 electron. Then now here you will find that now it is a completely filled. This is now 6 this orbitals sp3d2, okay, not sp3d2, total 6 sp3. Then now here what will happen? sp3d2 total 6. Then now 6 orbital given, 6f has given lone pair of electron. Then now over all complex you can see. Then now in a hybridized orbital, all are filled, means it is fully filled, but 3D is vacant, 4 electrons are there, 3D in that it is 4 unpaired, only one orbital is beginning, it is fully filled, 4 orbitals, 3D, 4 orbitals are unpaired from 3D. From 3D, 4 orbitals are unpaired. That's why it became magnetic, paramagnetic. It is paramagnetic due to these 4 unpaired electron. Okay. Then now I told you about these things, hybridization and geometry. This is also called, this is also same sp3d hybrid, now octahedral. This is also case of octahedral, but it is a high spin or a spin free complex. A spin free means it has a spin free complex, also called high spin. And in the beginning what I discussed, in case of cobalt NH3 there it was their low spin or spin paired, low spin or spin paired. Here it is a high spin, also you can tell a spin free complex. Now another example I want to tell you of nickel. Okay, then now this nickel I want to tell you, that is for nickel Cl4, nickel Cl4, and outside 2 minus is there, and nickel, with nickel 4 chlorine is attached, means NiCl4, and outside 2 minus. Then now here again, just to see what is the oxidation state of nickel, then see 4 chloride ion is there, then it means 4 electron it has given, 4 negative charge, but finally outside is 2 negative, then it means nickel is 2 positive plus 4 negative, then it means minus 2, that it is showing outside, it means nickel is plus 2. Now this time you write this electronic configuration of nickel having 2 electron less. What is the electron, this number, atomic number, just do minus 2, and then you write electronic configuration. Okay, then in outer electronic configuration means 3D, it will come 3D. In that now you will find that total 8 electrons will be there. In nickel, after deducting 3 electron, 8 electrons are there in d orbitals. Then 8 electrons, how it will arrange in d orbital? Then 5, 1, 1, 1 in each, then 5 it is over. Then 3 again it will paired, following the Hund's rule, it will paired. Then now out of 5, 3 are paired, and 2 are unpaired, means single electron. 5 plus 3, then 2 are unpaired in d orbitals. Then now here 4s is vacant, 4p is vacant, and in 3d 2 are unpaired electron, Then now here what will happen? Hybridization will take place in excited state. In excited state, always hybridization will take place in excited state. Okay, in case of cobalt F6 also, sp3d2 hybridization took place in excited state. Here also hybridization will take place in excited state, but here in hybridization S and P only taking part. S and P is taking part and it is forming sp3 hybrid. Okay, it will form hybridization is sp3, but orbital is called hybrid orbital sp3. Then now sp3 means total 4, 1s and 3p, total 4 orbitals. Then now 4 chloride will come, and chloride also 7 electrons are there. Then 3 pair are there, lone pair of electrons. Chloride has 3 lone pair of electrons, just like a fluoride ion. This is a chloride ion, same way. Then 6, then here 4 are there, sp3, total 4. Then 4 chloride will give 1 pair, total 8 electron. Okay, 4 pair, and then it will form complex. 4 pairs of electron is given from 4 chloride ion. Then now it formed nickel NiCl4 whole power 2 minus is there, 2 minus. This is high spin. Why it is high spin? Because now in 3D 2 electrons are there unpaired. Here 2 unpaired electrons are there in D. It has not taken part. It has not taken part in hybridization, only S and P. But in 3D 2 electrons are there. That's why it is called high spin or spin-free complex. Okay. In tetrahedral complex, 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. sp3 is there, then it will be tetrahedral, total including central metal it is 5. Then 4s are arranged in a space tetrahedrally. 3p, that in tetrahedral complexes 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. Oriented means arranged. It is arranged in that way. And here nickel is in +2 oxidation state, and the ions has electronic configuration outermost 3d8. The hybridization already I have discussed. Each chloride ion donates a pair of electrons. The compound is paramagnetic. Why paramagnetic? Because it has 2 unpaired electrons. Since it contains 2 unpaired electrons, that's why it is paramagnetic. Similarly, nickel tetracarbonyl NiCO4, nickel tetracarbonyl, same way you can write, but here oxidation state, outside nothing is there. Outside nothing is written, no charge, no positive, no negative, means it is a 0 oxidation state. Then NiCO4 has the tetrahedral geometry. 4 carbonyl is there, then obviously it will have tetrahedral geometry. But it is a dimagnetic. Why? Since nickel is in 0 oxidation state. 0 oxidation state means now that no charge is there. No charge is there. And d orbital is fully this thing. If you write nickel, the nickel, already I told you it has in the NiCl4, it was having a +2 oxidation state. Last was the 3d8 after removing 2 electron. Okay, but here in nickel carbonyl, what is its electronic configuration? That you write nickel electronic configuration. Now you have to not you can say remove 2 electron, you add 2 electron, correct? Then now here in this complex again it will be, because 4 carbonyl is there, it will form tetrahedral geometry. But it is a diamagnetic, since nickel is in zero oxidation state and contain no unpaired electrons. Electrons are not there. Okay. This all are paired, no unpaired electron. That's why it is diamagnetic. Now one more example I want to tell you. In the square planar complexes, the hybridization involved dsp2. Now only in these 4 orbitals, nickel you have seen, nickel tetracarbonyl. This here outer D has taken part, not only S and P. Okay, S and P has taken part. Now this in the planar complex, a square planar complex, here 4 orbitals are there also, but here inner will take part. Inner d orbital will take part. Okay, inner d orbital. Then in a nickel carbonyl, they have not taken part, inner. No, only S and P has taken part. Correct? 3D has not taken part, only 4S and 4P, 1S and 3P has taken part. But here D orbital, inner D will take part, inner D. That's why it will form DSP2. DSP2 hybridization it will take place. DSP2. And after hybridization, it will be called hybrid orbitals. DSP2 hybrid orbitals after hybridization. Then now in the square planar complexes, the hybridization involved is DSP2. One example is nickel CN4, outside 2 minus. Now you can understand why it is 2 minus, because each cyanide has 1 1. A CN4 is, each cyanide is 1 1 electron, then 4 minus, and outside 2 minus is there. It means nickel is plus 2. Here nickel is in plus 2 oxidation state, and electronic configuration easily you can write that here you will get 3D 3D8. Okay, nickel plus 2 means 3D8. Then again already you have written, I can say in a normal condition, electronic configuration is 5 or 5 first to write, 1 1 1 in all 5D, and 3 is 3 electron will paired, means 3 paired and 2 unpaired. In d orbitals, 3 will be paired and 2 will be unpaired, and 4s and 4p. Okay, actually here also S and P will take part, but extra things that D will also involve. Okay, in nickel tetracarbonyl, D has not taken part, 3D, but here inner is taking part, 3D. That's why name has been given DSP2. DSP2, D orbitals is also taking part, and name has been given DSP2. Okay, DSP2, and orbital will be called DSP2 hybrid orbital. Then now here you can say what will happen, that this before hybridization 2 are unpaired in D, then before hybridization these 2 electrons will paired, these 2 electrons will again paired, then 4 will be paired and 1 will be unpaired. 8 electrons was there, now all 8 is paired and 1 vacant is there. Out of 5, 2 into 4, 8. 4 are paired and 1 is unpaired. Then this happened in excited state, in excited state. Okay, and also you can tell when ligands approach to the central metal ion, then that time also energy change will be there. Okay, that due to that also it is paired. Then now one you can say d orbital is one d orbital is empty. One d orbital is empty. Then this one d orbital and s orbital and this 2p orbital will take part. One d, one s, one d, s and 2p. Total 4. 1s, 1d and s and 2p. Then total 4. 2p means 2 plus s is equal to 1 and d is equal to 1. Total 4. Then now hybridization is called DsP2. Total 4. Now cyanide will come and each cyanide will donate one lone pair of electron. Cyanide also have lone pair of electron. Then 4 cyanide will give 4 lone pair of electrons. Okay. Then now you can see in this case compound formed, complex ion formed, but they don't have any unpaired. No unpaired electrons are there, neither in D and nor in this hybridized. Nowhere in hybridized there will be no question of unpaired. Then in 3 and D also it is paired. That's why it is diamagnetic. Each of the hybridized orbitals receives a pair of electrons from a cyanide ion. The compound is a diamagnetic. You can see as is evident from the absence of unpaired electron. No unpaired electron, that's why it is a diamagnetic. Here one thing you have to note down. It is important to note that the hybrid orbitals do not actually exist. Very, very important. There is a hybridization is actually a hypothetical concept. Hypothetical. Actually it does not exist. But without this concept you can't give explanation of diamagnetism and paramagnetism. You can't give any explanation. You can't tell about the geometry. Then concept is important, but in fact hybridization is a hypothetical concept. It does not, this hybrid orbital does not exist. Okay. Then this is important to note that the hybrid orbitals do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. Okay, it is only manipulation, mathematical manipulation of wave equation. Then now I am stopping only here. Next class I will discuss magnetic properties of coordination compounds. Thank you.